I would like to take a minute to talk about the use of significant figures, especially when you're working with scientific notation. As I said before, there will be a few places in this course where we will be doing a calculation, but I really want to emphasize I want this course to be an enjoyable experience for you. And I realize you guys are, for the most part, not math and science majors. So there will be a few calculations, but I will be here to hold your hand throughout the process. And if you have any question at all, please feel free to reach out to me. And as I said before, I honestly mean it. If you were to hypothetically skip everything that involves a calculation in this course, I promise you it is still very much possible to have a grade that's just fine. I don't want to make specific promises because every case is unique, but don't let the math scare you, especially for the second half of this course. There's basically no math at all in it. So in the few times in this course where we do need to do a calculation, I'm going to say the numbers we work with, you could always round to 3 digits, and that will be considered good enough. Don't write out, if you enter something in a calculator, you get a long string of numbers, round after the second or third number and be done with it. Don't write out 20 strings of random numbers. It's annoying to work with. It's not nice for me to see. It makes my dog whimper. None of us like it. So what do I mean by that? As an example, let's take the speed of light. If I want to include 9 digits when I write out the speed of light, I would say light travels at a speed of 299,792,458 meters per second. This number I just quoted is a very exact number. Usually in practice, we would just say, well, here's a 2 and a 9 and a 9 and a 7 and a 9. I'm just going to round up to 300 million and be good. I would have, because 7 would round up, turn that into a 0, into a 0, into a 3. So to demonstrate this idea, let's take Einstein's famous equation E equals mc squared. Now, let's not worry about what this equation really means or the significance of it. Let's just plug in the speed of light and see what happens. So in this equation, c is the speed of light. So we'll take a number that is the speed of light and square it. M is the mass of an object that we're considering, and E is the object's rest energy. So it's kind of, if I were to hypothetically turn all of that object into pure energy, how much energy would I get out? This equation tells me that. So when you perform a calculation, round the numbers you're working with to 2 or 3 digits. I usually go to 3, but you could do even 2 is just fine. So as an example, let's suppose we have a ball that has a mass of 2 kilograms. So I'm going to plug this ball. My mass is 2 kilograms. C is the speed of light. We're going to use the exact value of the speed of light in magenta. We're going to use the approximation for the speed of light down here in green. And let's see what happens. So, okay, I could plug E equals 2 for my mass and the exact value for the speed of light squared over here. The rest energy here, I have 2 kilograms for my mass and 300 million meters per second in squared in green. I hit enter on my calculator and I get the rest energy of the ball. Here in magenta is the exact value. Here in green is the approximation. Now let's see, where would we round? Well, 7 would round up the 9 up to a 0. Then we have an 8 here. So if I compare these two numbers are less than 0.1% different. So literally what that means is this approximation in green is less than 1/1000th off from this exact value in magenta. And entering the numbers in green down here is just easier to work with. It's easier to see what's going on. Seeing what's going on is very good because it lets me give you lots of partial credit, which is a wonderful thing. So using the exact values is just easier to work with mathematically. It's easier to track into a problem. And as long as a precision of 1 part in 1,000 is considered good enough, which I'll tell you right now will always be the case for this course, then just use the exact value and round the numbers that you're working with. So to finish off the first chapter, I'm going to look at the typical sizes, or in other words, lengths or distance scales of different objects in the universe. And we're going to be looking at them in scientific notation. Now, many of the pictures and objects were taken from scaleoftheuniverse.com. It's a very lovely website. If you ever are studying really hard and you need a mental break, it's relaxing music. You could zoom in and out. You click on the objects they show you. You could read something interesting about it. It's a very amusing website when you have 5 minutes to kill. So, the characteristic size of quarks. Quarks are particles that make up particles that make up atoms. So quarks are the smallest unit of nature that we are currently aware of. It may be possible that there are even smaller things that make up quarks, but as of right now, those are just hypothetical. We do not know of any that actually exist. So the typical size of a quark is about 10 to the negative 18 meters. You could see down here that I am using scientific notation because it's much easier to write 10 to the negative 18 than 0.00001 meter across. Also, this 10 to the negative 18, I see the number 18 here. That immediately tells me how many jumps I would need to make for my decimal, and that right away tells me how many zeros I'm dealing with. So, if I increase the distance scale that I'm looking at by a factor of 1,000, I am talking now about the typical size of the nucleus of an atom. The nucleus of an atom is the center of the atom. It contains protons and neutrons that are tightly bound together. And I know I'm jumping up by a factor of 1,000 because 10 to the negative 18, 10 to the negative 15, I gained a factor of 10 to the 3, and 10 to the 3 is 1,000. So the characteristic distance between the protons and neutrons, the distance across the size of an atomic nucleus, is about 10 to the negative 15 meters. If I want to look at the typical size of an atom itself, that's going to be about a factor of 100,000 times bigger. I jumped from 10 to the negative 15 to 10 to the negative 10, so that's a jump of 10 to the 5 times bigger. If I write 10 to the 5 out, I would have a 1 followed by 5 zeros. That's 100,000. So the typical size of the center of an atom is around 10 to the negative 15 meters. The typical size of an atom from one side of the electron orbit to the other is about 10 to the negative 10 meters. So the picture over here, drawn in the upper right, is very much distorted. The nucleus in this picture would have to be much, much smaller. To put it in context, if the nucleus of an atom were the size of a grape, then the electrons orbiting the nucleus would be little tiny grains of salt, or maybe even smaller, orbiting around the upper deck, way in the nosebleed at the top of the stadium. So that's kind of a scale for the typical size of an atom. Now, if we increase by a factor of 100 times bigger, from 10 to the negative 10 to 10 to the negative 8, then we are looking at the typical sizes of some viruses. And if I go from 10 to the negative 8 meters across to 10 to the negative 6 meters across, I'm looking at the typical size of some bacteria. If I increase that from 10 to the negative 6 to 10 to the negative 10 to the negative 4, then I'm talking about the characteristic thickness of paper. Now, before I go on, I just want to stop and point something out that I'm doing. You might say, well, what about the number in front? Here I have 4.2, here I have 2, here I have 1.5. I was only saying 10 to the negative 8, 10 to the negative 6, 10 to the negative 4. The reason I'm doing that is I'm not so much worried about the first number in front. The second number, the 10 raised to a power, that really gives you an idea of the typical size of the number that you're working with. To give an example, if I gave you $10, that would be a pretty good day. You'd be happy. If I gave you $15, that'd be a pretty good day. If I gave you $8, that would be a pretty good day. All of those numbers are more or less around 10. Now, compare your reaction there to what if I gave you $100, or what if I gave you $125 or $200? your reaction would be orders of magnitude better. And if I gave you $10,000 or $12,000, your reaction to those two scenarios would be even better still. So the typical reaction giving you 10-ish dollars compared to the typical reaction to giving you 100-ish dollars versus the typical reaction to giving you 10,000-ish dollars, that's really what we're looking at. We're not really worried about this first number in front. We just want to get a feel for the typical size of these objects. Now, if I go up to 10 to the negative 3 meters, that is a millimeter. That's the smallest increment on a ruler that has metric measurements on it. And we're now beginning to talk about something comparable to the size of an ant. If I go up by a factor of 1,000, 10 to the negative 3, and then 10 to the 3 times bigger, I have something on the typical size of a human being. And if I increase that by about a factor of 100, give or take, I'm talking about something comparable to the Statue of Liberty. Now, if we want to go higher still, the largest dune in the world is about 325 meters tall, give or take. And the diameter of the state West Virginia is about 10 to the 5 meters across. So West Virginia, it's a state. I have a typical feel for how big it is because I have driven across it and driven across some of the other states, Ohio, Pennsylvania, New York. They're more or less 10 to the 5-ish meters across. Some are bigger, some are smaller. Now, if I increase by a factor of 10, we're talking about the diameter of the moon measured in meters. And if we increase by a factor of 10 again, we're talking about the diameter of the Earth. Now, I'm not saying I am multiplying the diameter of the moon by 10. I'm saying turn this from a 10 to the 6 into the 10 to the 7, and you go from talking about something comparable in size to the moon to something comparable in size to the Earth. We could go up more. If we increase the size of the Earth by a factor of 10-ish, then we will be talking about one of the larger planets in the solar system like Saturn. And if we increase Saturn by a factor of 10, now we're beginning to talk about the typical size of a star like the sun. If we increase that by a factor of 100, I'm going from 10 to the 9 to 10 to the 11. That increases by 100. I'm talking about the typical distance in the solar system from the sun to a planet. 1 AU specifically is the distance from the Earth to the sun. So that is about 10 to the 11 meters. Times 1.5. If you want to move out to the furthest man-made object away from the Earth, you would have to increase your distance scale by a factor of about 100 times larger. In the early 70s, the Voyager space probes were launched. Voyager 1 traveled by Jupiter and Saturn, shot up and out of the solar system. Voyager 2 traveled to Jupiter, then Saturn, then Uranus, then Neptune, and now is traveling towards interstellar space. And currently, Voyager 1 is the furthest man-made object away from the Earth at about 10 to the 13 meters away. Coincidentally, Voyager 1, the distance from Earth to Voyager 1 is also comparable to the size of the black hole that was directly imaged at the center of galaxy M87 a few years ago. So for context, if the sun were located at the center of the black hole that was imaged, then Earth's entire orbit would be inside the black hole, and Mars's orbit and Jupiter and Saturn's orbit would all be inside that black hole. Pluto's orbit would be inside that black hole. The furthest man-made object away from the Earth would barely be outside that black hole. Now, this is, of course, ignoring the fact that the black hole wouldn't let anything escape, on, but this is to give you an idea for the context of the distance scales that we're talking about and just the sheer size of this black hole at the center of that galaxy. Our galaxy has a very large black hole at its center too. I think it's very large. I don't think it's as big as this black hole, but it's still pretty big. If we increase our typical distance scale by a factor of 1,000 from 10 to the 13 to 10 to the 16 meters, then we're talking about the distances to the nearest stars. And if you remember from the Cody's Lab video, if you have a P at one location and the next star is another P about 130 miles away, these are the distances between the stars. So the nearest star, Alpha Centauri, is actually a triple star system. There's Alpha Centauri A and B, which from the Earth, you could only see one star if you're not looking through a telescope, if you're just looking with your eyes. Alpha Centauri A is a little bit bigger than the sun. Alpha Centauri B is a little bit smaller than the sun. Then there's the dwarf star Proxima Centauri, which is super dim and a little bit closer, but these are all about 10 to the 16 meters away from us. The typical diameter of a large galaxy like our own is about 100,000 times larger than that. We're increasing by a factor of 10 to the 5, from 10 to the 16 to 10 to the 21. And this is the diameter of the disk of our barred spiral galaxy. Then the typical distance between large galaxies in our galaxy cluster is about 10 to the 22 meters. In about 4.5 billion years, the Andromeda Galaxy is going to collide with our own galaxy. Right now, the Andromeda Galaxy with its spiral arms are about 5 times larger than the full moon. But we can't really see the spiral arms because the spiral arms are very, very dim, that they're just not easy to see. But they are technically, they take up a bigger area on the sky than the full moon. It is possible to see the core of the galaxy from Earth without the aid of any telescope. If we increase by a factor of 10 again, you're now looking at the size of our small galaxy cluster. Our small cluster has about 2 large galaxies in it, then a bunch of smaller galaxies. It's about 10 to the 23 meters across, give or take. And if you want to increase by a factor of 10 again and a few more, you're looking at the size of our galaxy supercluster Laniakea. The distance to the edge of the observable universe, the distance that it is not possible to see beyond, is about 10 to the 26 meters. So that's about 100 times larger than this. Now, what do I mean by the edge of the observable universe? Well, it takes light time to travel from point A to point B. I sometimes articulate this as I ask, what happens first, thunder or lightning? And I wait, sometimes people will say lightning occurs first. And then I say, no, lightning and thunder occur at the same time, but we observe lightning first because light travels really, really fast, practically instantaneously if you're talking distances comparable to miles. But it takes sound time to travel. Sound travels, it's about 6 seconds to a mile for the sound to reach you from where the lightning struck the ground. Now, when you're talking distances on Earth, it is a good enough approximation to say light travels approximately instantaneously. But if you're talking astronomical distances, it does take light time to travel. So you could imagine right after the Big Bang, a particle of light was emitted right over here, and then that light has been traveling towards us for the longest possible time. So you have a particle of light traveling from here towards us. It's traveling at the greatest possible speed, which is the speed of light, and it's traveling for the longest possible time, the age of the universe. And it is just now reaching us. There very well are galaxies and stars and planets and other things out here, but traveling at the speed of light, they are just so far away that they were not able to reach the Earth yet. So it's not that they're not out there. The age of the universe just isn't enough for that light to have reached us yet. So this is what we mean by the distance to the edge of the observable universe. Now, if you notice, often it's said the universe is about 13.8 billion light years. What's the deal? This says 46 billion light years in radius. This has to do with the fact that space is expanding. If you want to ask me about that, either send an email or ask in lecture and we could talk about that. But this actually can be reconciled. This 46 billion light years away number is reconcilable with the age of the universe being 13.8 billion years old. You just need to account for the expansion of the universe itself. Now, What is the shape of the universe? There are some hypotheses that the universe might be infinitely large, or maybe the universe is finitely large. And if you travel out in a certain direction, you will eventually wrap around and come back to your starting point. Think about the curvature of the Earth. If I stand at one location on the Earth and I start walking, eventually I'll come back to my starting point. That is a consequence of the Earth, the surface of the Earth curving around on itself. It is possible that the universe does something similar. Now, we do not know if the universe does that versus if the universe is infinitely large, but we can put a lower limit on the size of the universe if the universe is not infinitely large. And the lower limit on the size of the universe is about 10 to the 27 meters across. So this is the end of chapter 1. I will begin the next section in this course in the next video.